Alright, hello everyone. I am back with another past paper walkthrough because the first one was just so fun and I felt like doing another one. Alright, yeah. So this is October-November 2015, paper 1-1. Actually, paper 1-1 is the same as paper 1-3 for winter 15, so if you're doing 1-1 or 1-3, both are the same. It's in this for this winter 15 did the same. I mean, not every year, but yeah. And yeah, it's chemistry 9701. So let's start. How about that? Question number 1. The table gives the successive ionization energies for an element X. What could be the formula of a chloride of X? Well, let's see what the biggest jump is. The biggest jump, according to me, seems to be in 5th and 6th ionization energies, is it not? But if you want, you could calculate them out if you're not able to see the trend easily. However, for paper 1, you have to be fast, so better if you are able to identify the biggest jump immediately, but you can calculate them out as well. So 27 minus 1800 is 900, 4800 minus 2700 is 2100, so that's a jump of 2100. 6000 minus 4800 is plus 1200, and then 12,300 minus 6,000 is plus 6,300. So that's obviously the biggest jump. It's quite a big jump compared to these all, right? So that means that this X has 5 electrons in its valence shell, right? Just like but what can I think of? Cl. I feel like I remember one compound which is like PCl5 and there's also PCl3, right? Because if you see the options, like I mean XCl4, why can't you take XCl4? Because that means Cl, right? So they're like, it's bonded to 4 chlorines, and that means it has one random lone pair, and that's quite weird, is it not? But maybe it's like PCl5, wherein you have X attached to 3 Cls, and so it's bonded to 3 chlorines, but then it has a lone pair, which is a viable option, don't you think? So I feel like the answer should be C. XCl2, again, like it has Cl, so it's attached to bonded to 2 chlorines, and then it has one lone pair, but then one random electron there, which is just weird. Don't you think it's weird? I feel like that's quite weird. And then if you look at XCl, so it's bonded to 1 chlorine, and then it has 1, 2, 3, 4, so it has 2 lone pairs, which is, I suppose, that could be possible, but I feel like the most likely option is C, don't you think so? Just because like I have one, I can think of a compound just like XCl, like just like this X thing that they've stated here. I told you, like 5 valence shell electrons. I have PCl3, which is like, it looks like XCl3, don't you think? So because like I can compare it to PCl3, I feel like the best option should be C. Alright, so yeah. Next question. Which set of conditions gives the highest yield of ammonia at equilibrium? Catalyst, absent, present. Well, a catalyst should not really affect the yield, should it? Because what does catalyst do? It lowers the activation energy, doesn't it? So that means that more number of reactant molecules have energy that is greater than or equal to the activation energy, right? But that doesn't mean the yield changes. That just means that the rate of reaction increases, but the yield is still the same, right? So that means it doesn't really matter if the catalyst is absent or present, my yield will still be the same in terms of like if a catalyst is added or not. Then if I look at pressure, well, on all like left hand side and right hand side, I just have gases, so I can compare the moles of the gases. So I have 4 moles of gases on this side, 3 plus 1 is 4, and then I have 2 moles of gases on this side, right? So what does that mean? That if I want to shift my equilibrium to the right hand side, what should I do? Well, since the right hand side has fewer moles, that means I should increase the pressure, right? Because if pressure increases, equilibrium will try, according to Le-Chatelier's principle, equilibrium will try to oppose the change to the increase in pressure by shifting the equilibrium to the right hand side. Why? So that there are a lesser number of moles in the mixture, right? The closed system where you have N2 and H2 and NH3, so you'll have less moles if your equilibrium shifts to the right hand side, and less moles means what? Means lower pressure. So equilibrium tries to oppose the change, the higher pressure, by lowering the pressure by shifting it to the right hand side, which means you get more ammonia formed because your right hand side is ammonia, right? So pressure should be high. temperature. They have said that delta, what have they stated? They've stated that delta H is standard delta H is minus 92 kilojoules per mole, which means that this is exo and this is endo, right? The forward reaction is exo, the backward reaction is endo. So if the forward reaction is exo, how will it be favored? It will be favored by low temperature. Why? Because if your temperature is lower, equilibrium will try to oppose this change in temperature by releasing more heat, right? Releasing more heat. And which type of reaction releases heat? That is an exothermic reaction, right? Which means your forward reaction. So your forward reaction is favored, and more heat is generated, so that equilibrium is re-established, so that more heat is generated, which means the temperature is increased back to the equilibrium condition level or something. You can say that. So equilibrium is re-established, right? So that means that your answer must be where there are 3 ticks, which is A. Done. And next, use of the data booklet is relevant to this question. The compound S2O7 is hydrolyzed by water to produce sulfuric acid and oxygen only. So I've constructed this equation. Let's balance it. S2, so I should have 2 sulfurs, and then how many hydrogens do I have? I have 4 hydrogens, so I should make this 2 as well. 7, 8, 9, so I have 9 oxygens on this side. On this side I have 10 oxygens, so let me make this 1 by 2, so that now I have 4 to the 8 and 9 oxygens. Alright, it's balanced now. Which volume of oxygen measured at room temperature and pressure is evolved when 0.352 grams of S2O7 is hydrolyzed? So I have 0.352 grams. So what is my thought process? My thought process is I can find out what the MR of this compound is. Then when I find out the MR, I can use the formula N equals M over MR, so moles equals mass over MR, to find the moles of this compound. Then the ratio of this to oxygen is 1:1 by 2, which means the moles I get for S2O7, if I divide them by 2, I'll get the moles of oxygen produced, right? And if I get the moles of oxygen produced, well, they said it's at room temperature and pressure, right? So V is equals to, or actually you can say moles equals, you can use the formula N equals volume over 24, because they have stated that is room temperature and pressure, so I can use this formula. And then V equals to 24, and you don't need to add the 0.0. I'm just a weirdo. I like to add 24.0, right? It's paper 1, who cares? So yeah. Anyways, let's calculate the MR of this. So MR should be the MR of sulfur 32.1. You have 2 sulfur atoms, so 30.1 into 2, and you have MR of sorry, not MR, I mean AR. It should be AR. My mistake. But yeah, AR of sulfur is 30.1. AR of oxygen is 16, and then times 7, because you have 7 oxygen atoms. Now if you do that in your calculator, you get 16 into 7. Yeah, that should be 176.2 grams per mole. All right, so that is my the unit of MR is, by the way, or AR is grams per mole. So yeah, so now if I want to find moles, then that will be mass over MR, so that will be 0.352 divided by 176.2, right? So 0.352 divided by 176.2. If you want, you can see the unit cancellation over here. I'll make it for you. So that gives you, and then this will go to the numerator, so you get the unit of moles, which is mole. Lol, quite a circular definition, I suppose. Not a circular definition, but a circular explanation. Anyways, let's ignore that. And 0.352 over 176.2 is 1.9977 into 10 to the power of, I'm going to add some dots because just so that it's recurring, not recurring, but like more decimal places. That is recurring, isn't it? Anyways, not recurring, that's more decimal places, whatever. 1.9977 into 10 to the power of minus 3 moles. Alright, this is the moles of S2O7. So now if I want to find the moles of O2, it should be half the moles of S2O7, right? So what will that be? I'll just divide the value I have by 2, and I get 9.9886 approximately into 10 to the power of minus 4 moles. All right, so now I want to use the relationship I showed you before, N equals V over 24, so V equals to 24N, right? So V equals to 24 into this value that I've gotten, 9.9886 into 10 to the power of minus 4. So what do I get? And also note that they have written, let me just do this calculation first and then I'll tell you what I'm saying. So answer into 10 to the power of minus 4. So what did I do? 9.9886 into 10 to the power of minus 4. I made a mistake. Anyways, into 24, that's what I meant. Yeah, so I get approximately 0.02397 dm cubed. I actually rounded it off. I did not use the calculator value, so that's my mistake, but I don't know if that's right. Anyways, but that's roughly the value. All right, But note that this is in dm cube and my options are all in cm cube. So what is the conversion from dm cube to cm cube? You should have it memorized at this point. It's into 10 to the power of 3, or it's into 1000, and from cm cube to dm cube it should be divided by 1000, or you can say into 10 to the power of minus 3. Right, so I like saying that it's into 10 to the power of minus 3. The reason for that is that 1 meter is 100 centimeters, right? And 1 meter is also 10 decimeters, right? Because decimeter means 10 to the power of minus 1, centimeter means 10 to the power of minus 2. All right, so 1 meter is 100 centimeters, 1 meter is 10 decimeters, which means that if you compare centimeters to decimeter, then 1 decimeter is actually 10 centimeters, is it not? I think that's quite obvious. This is 1 0 and this is 2 0, so 1 decimeter is 10 centimeter. But now you're talking about 1 dm cubed, so it should be 10 cubed cm cubed. So the conversion from dm cubed to cm cubed is multiplied by 10 to the power of 3. And if you want to convert from cm cubed to dm cubed, you will do the opposite thing, which is into 10 to the power of minus 3. All right, so my point is that if I want to convert this to dm cube, I'll just do 0.02397 times 1000, so I get 23.97 cm cube, which is approximately 24 cm cube, is it not? Which means my answer is B. Great. All right, so that is the answer, and let me erase my beautiful artwork over here, and yeah. Next question. Nitrogen N2 and carbon monoxide CO both have MR 28. All right, so they have equal MR. The boiling point of nitrogen is 77 kelvins. The boiling point of CO is 82 kelvins. If you have like, you can easily see that nitrogen is like this. This is the molecule of nitrogen, and CO is this molecule, right? So what is the difference? The difference is that over here you have no electronegativity difference, so it's just van der Waals forces, or you could say temporary dipole induced dipole forces, right? So you only have temporary dipole forces, which means it has a much lower boiling point compared to CO, where the 5 most electronegative elements are FO and ClBr, aren't they? So N is O is one of them, and so you have partially negative O and partially positive C, which means you have an electronegativity difference, which means you have permanent dipole forces over here. Or you could say, what are the other names for it? Dipole forces? I don't remember the exact names, but I use permanent dipole forces as the name. So yeah, you have that. Obviously, you do not have hydrogen bonding because you have no hydrogen here, but you have permanent dipole forces, which means it must have a higher boiling point because it has stronger intermolecular forces, right? Is it not? It has stronger intermolecular forces. So what could be responsible for this difference in boiling points? Let me just actually have to go because the bell rang. Sorry. Okay, yes, sorry, I'm back. Someone was at the door. So yeah, so what I explained this, right? So what could be responsible for this difference in boiling points? Let's see the options now. CO molecules have permanent dipole. The N2 molecules are not polar. That's literally what I said. Yeah, this is polar, this is non-polar, right? So N2 has sigma and pi bonding. CO has pi bonding only. Well, actually no, because both of them have sigma and pi bonding. See, this first one is sigma, but then any of them will consider to be the first one, but one is sigma and the other two are pi, right? That's what makes up a triple bond. And over here as well, you have one as sigma and the other two as pi. That's what makes up a triple bond. So that's wrong. N2 has a strong N and triple bond. CO has a C double bond O. No, that's wrong. Both of them have triple bonds. The CO molecule has more electrons than the N2 molecule. Well, they both have MR 28, so you can't really compare them on the basis of MR or electrons, can you? And that explanation only you use when you are comparing, two compounds that have, like, both of them have temporary dipole forces. So then you can compare them on the basis of number of electrons or MR, anyways, like C, let me just count the number of electrons. C will have 4 electrons, O will have 8 electrons, right? So that is 12. And sorry, not 4, 6. What am I saying? The valence shell has, so it should be 6 in total, and this should be 8 in total, so that becomes 14. Obviously, I'm sorry about that. And then NN has how many electrons? And one N atom has 7, so 7 times 2 is 14 as well. So both of them have 14 electrons actually, and both of them have the same MR, obviously. We can deduce it from that as well. They have the same number of electrons, and so the answer has to be 80. Yeah? Alright. Some carpanes contain small flakes of silica, SiO2. In the structure of solid SiO2, each silicon atom is bonded to X oxygen atom. So SiO2, which is, you know, the simplified formula would actually say Si2O4. You can write it as that, I suppose. So Si2O4, what does that mean? That each actually, you know, because like each silicon atom is actually bonded to 4 oxygen atoms, and this should be drawn like this, I suppose, better, but you know, yeah. So it's 4 oxygen atoms, and each oxygen atom is bonded to how many silicon atoms? Each oxygen atom is bonded to yeah, so it's sort of like this. I'm not drawing the whole thing, but you can see here that each oxygen I have, like for example, this oxygen is bonded to 2 silicon atoms, and each silicon atom here is bonded to 4 oxygen atoms. Am I right? So that means 4 over here, and each oxygen atom is bonded to 2 silicon atoms. And then what is the third statement? Each bond is a Z-type bond, but you do not have ionic bonds here. You only have covalent bonds, and that is, you know, you should know that by this point. You've already studied this in IGCSE, I suppose. So then the answer is C, right? 3 tick marks. So yeah, C. Solid sulfur consists of molecules made up of 8 atoms covalently bonded together. So that they're just saying that it exists as S8 naturally. The bonding in sulfur dioxide is SO, like that, SOO, alright, and it has 6 electrons in its valence shell, 4 are used in bonding, and then it has 1 lone pair as well, alright. So what does that mean? It has, so its steric number is, I don't need to do this, but I'm just doing it because I just feel like explaining this part as well. So it has 1, 2, 3. So two bond pairs that are sigma. You do not count pi bonds when you're calculating steric number. 2 bond pairs that are sigma, and you have 1 lone pair, right? So steric number is 3. So it has sp2 hybridization, but its bond angle is not 120. It's 120 minus 2.5 because of the, you know, the lone pair. 120 minus 2. Each lone pair reduces the bond angle by 2.5 approximately. So 117.5 degrees is the bond angle. Anyways, it's not a question about bond angle stuff. This is a question about enthalpy. Yeah. So the enthalpy change of combustion of S8 solid is minus 2376 kilojoules per mole. So let's just write that down. So S8 solid plus O2 gaseous, giving you SO2 gaseous. That is your enthalpy change, is it not? And it's for 1 mole of the acid solid. That's how you define enthalpy change of combustion. 1 mole of the substance is reacting with an X oxygen, right, to form combustion products, right? So this will become 8 SO2. 8 2s are 16, so that means I will add an 8 over here to balance the equation out. And then what? So this reaction, this change, they have shown that its value is what? Minus 276 kilojoules per mole, right? I'm not bothering writing with the units, but you can write the units if you want to. Energy required to break 1 mole of S8 solid into gaseous atoms, which is what I have here. I have 1 mole of S8 solid into gaseous atoms. That is, this change is plus 2232 kilojoules per mole. And now I have 8S gaseous over here. Alright, and then they have given me the OO bond enthalpy, which is 496. So again, I can make or maybe it's better if I just make 1 arrow here. So just 1 arrow going from both of these. So I have plus 2232, and then for oxygen I have another enthalpy change, which is OO bond enthalpy. So what does OO bond enthalpy mean? It means that this OO bond is broken, right? And I get individual free O atoms, right, from that bond. So I have 8 OO bonds here, don't I? So that means this value, which is 496, the OO bond enthalpy is 496, I will multiply it by 8. Alright, so that is what I have in this arrow. And then what do they want? They want me to find out what is the value of the SO bond enthalpy, and how many SO bonds do I have actually, and 8S gaseous plus what should I say, 8 to 16, so 16O gaseous, right? So yeah, so this is my enthalpy cycle that I have. So over here I have 8s plus 16O breaking down, and over here I have also 8s plus 16O, because that's what they want me to find. They want me to find what is the SO bond enthalpy, and they've shown me as well the structure is OSO, and I have 8 of OSO, which means I have 16 of this bond, right? I have 16 of the SO bond, right? Because 2 per molecule. So 16 SO bond means I have 16x. Let me just take it as 16x. All right. So now now that I have my Hess's cycle, I can just take one route and the other. All right. So let me take one route. I'll just make it simpler for myself, perhaps. That one route I'm taking as this one. So 16x. All right, and the other route I'm taking as this one. All right, you can really start from anywhere, I suppose, but this is how I'm doing it. So this is my other route. Okay, and so A16x is equals to what? So the enthalpy change for both the routes should be the same, right? Whether the final initial condition, the reaction condition, the same, which they are. So I am going against the arrow over here, right? Like this arrow is going in this direction, but my route is going against that arrow direction. So it means my minus 2376 becomes plus 2376. All right, and over here I'm going in the direction of the arrow, which means I will keep the signs as they are. So I have plus 2232 plus, now this one is 496 times 8. So let me just calculate it out. What is 496 times 8? That's 303,968. So I will write that down as well. 2232 plus 3968. Okay, so I'll calculate this out. 16x is equals to 2376 plus 2232 plus 3968, and that is plus 8576. X is equals to what? Answer divided by 16, right? So that is plus 536 kilojoules per mole. And how do I know that this answer is right? It's because bond enthalpy values are always positive, because bond enthalpy refers to bonds broken, right? Like 1 mole of, like when you break 1 mole of covalent bonds, right? That are gaseous. What does that mean? That means that my answer is right. That's one way of verifying your answer, that if you get a positive answer for bond enthalpy, that means you could be potentially right. Anyways, all the options are positive, so that doesn't really help, but my answer is D. Alright, I got D as my answer. Yeah, that is the answer. Next question number 7. Let me just put my charger, plug my charger in. Alright, next question. Question number 7. Use the data booklet is relevant for this question. In an experiment, the burning of 1.45 grams, 0.025 moles, they've conveniently given me the moles value as well already as well, of propanol was used to heat 100 grams of water. The initial temperature of the water was 20 degrees Celsius and the final temperature of the water was 78 degrees Celsius. Which experimental value for the change of combustion for propanol can be calculated from these results? So E is equals to minus mc delta T, right? Or in fact, actually, as I told you before in my previous paper walkthrough, T represents thermodynamic temperature, which is in Kelvin. Theta represents temperature in degrees Celsius. But the thing is, I have delta T here, so it doesn't make a difference if it's delta T or delta theta, because temperature difference is the same whether it's in Kelvin or whether it's in degrees Celsius, because you're just subtracting one temperature from the other, which is, it's going to be the same whether it's in Kelvin or Celsius. It doesn't matter. So you can write MC delta T, or if you want to be more precise, you can just make it MC delta theta. Alright, whatever. I'm going to make this Q as well, that's fine. Anyways, I'm just going to keep it as E equals MC minus MC delta T. Alright, and so over here your mass should actually be your mass of water, so minus 100 into what is my C value. I'll just get it from the data booklet, okay, because I don't know how many significant figures to take it as, but the data booklet have that. Okay, so according to the data booklet, it is, where is it? Okay, there it is. So 100 grams times 4.18 joules per kilograms per Kelvin. And then you have, actually no, I'm going to take it as 4.18 joules per gram per Kelvin. Sorry about that, my mistake. And then the delta T is going to be 78.0 minus 20.0, which should be 58.0, right? Yeah. 78.0 no Kelvin, because I told you even if you convert this to Kelvin, so 78 plus 273 would be 351, and then 20 plus 273 would be 293. So 351 minus 293 would still be 58 kelvins. All right, so it doesn't matter if you do it in Celsius or Kelvin. And then these units all cancel out, don't they? So I get my answer as minus 4.18 into 100 minus 418 joules. Sorry, why did I forget to multiply this by 58? That is minus 24244 joules, right? But then the thing is that they've given me the calculations in kilojoules per mole. So the first thing I should do to convert from joules to kilojoules is divide by 1000. So that gives me minus 24.244 kilojoules. And secondly, they've given me kilojoules per mole, which means I also have to divide by the number of moles I have. And the number of moles, the limiting factor, actually the moles of propanol, right? So they've already given me that as 0.025. So let me just divide the answer I've gotten here. Kilojoules divided by 0.025 moles. So what do I get? I get minus 969.76 kilojoules per mole. And so is that an option? That is an option, because this is approximately minus 970 kilojoules per mole, which is my option B. All right, so that is my answer. And what does the negative sign represent? The negative sign represents that it's an exothermic reaction. That's the that's the point of keeping a negative sign here, that you know, if you get your delta T, because you got a positive delta T, right, which means that you must have an exothermic reaction, right? So this helps to make the, again, I don't know what to call it, the bookkeeping easy, whatever. But yeah, so it's an exothermic reaction, and the answer is B. Next question. 8. Which row correctly describes the electrodes that can be used in a diaphragm cell for the production of chlorine, hydrogen, and sodium hydroxide, which is basically, you know, you're doing electrolysis of brine, which is concentrated, what is it, concentrated NaCl, am I right? I literally don't even remember what brine was. I think it should be concentrated NaCl, right? Yeah, it's concentrated NaCl. Why did I? Yeah, it's concentrated NaCl. Anyways, but the thing is that this was removed from the AS chemistry syllabus. Electrochemistry is not in the AS chemistry syllabus, and it is in the A2 syllabus, but I think this thing, like what is the anode and what is the cathode, those are not in the syllabus anymore, like in the whole A-level syllabus. So it doesn't really matter, you can skip this question. But if you want to know the answer, according to the mark scheme, because I don't have this by heart because I didn't learn it, but the answer is D. So you use a titanium anode and a steel cathode. I suppose the logic for that is something along the lines of, you know, steel, it has iron, and like if you use steel as the anode, then you will have chlorine produced as well, so they could react or something. Honestly, I don't know the exact logic of using titanium or steel. If you know it, then kindly put it in the comments. Otherwise, it doesn't really matter according to the syllabus, but you know, it's good for general knowledge. So if someone could write in the comments, that would be great. Or maybe I'll check it on the internet later. And nevertheless, the answer is D. So yeah, maybe it's just a memorization thing that you should know it, but there must be a reason behind it, obviously. Hexamine, question number 9. Hexamine is a crystalline solid used as a fuel in portable stoves. Great. The diagram shows this, well, actually portable stoves, I don't know if they're weight or not, incident pollution. Anyways, diagram shows its skeletal structure. What is the empirical formula of hexamine? So empirical formula is the simplest whole number ratio, right? So I have 1, 2, 3, 4. I have 4 nitrogens, so let me write N4. And then how many carbons do I have? Carbon is at every junction, so this 1, 2, 3, 4, 5, 6. I should have 6 carbons. So that makes it C6. And then how many hydrogens do I have? Because whenever I have carbon, because carbon in organic chemistry, carbon forms 4 bonds all the time, right? So most of the time at the very least. So that means you should have 4 bonds. So wherever carbon, carbon, for example, it has 2 bonds, but wherever is left, those 2 bonds would be hydrogen. What I mean is, for example, over here, this carbon has 2 bonds, right? But there are 2 bonds left for it to form. So those 2 bonds are actually hydrogen. All right. So I have 2 hydrogens there, 2 more hydrogens there. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12. So basically double the number of hydrogen atoms in this case, carbon atoms in this case. So we have N4C6H12. Can I simplify that further? Because they've asked me for the empirical formula. Yes, I can simplify it further. I can divide this by 2. So I get N2C3H6. Now, is that an option? That is an option. That is option B. C3H6N2. So that's my answer. Alright? Question number 10. A mixture of nitrogen and hydrogen gases at a temperature of 500 kelvins was put into an evacuated vessel of volume 6 dm cubed. Temperature of 500 kelvins. Okay, the vessel was then sealed. So it's a closed system, meaning it can get to dynamic equilibrium. The mixture was allowed to reach equilibrium. It was found that 7.2 moles of N2 and 12 moles of H2 were present in the equilibrium mixture. The volume of the equilibrium constant Kc for this equilibrium is 6 × 10⁻⁻² at 500 kelvins. Okay, so let me just write down the value. So what is concentration? Concentration is moles divided by volume, right? So it should be, for example, for N2 it will be 7.2 divided by 6.0. Alright, so I'll just write them down over here. So I have 7.2 moles of N2, right? So let me just make it 7.2 divided by 6.0 moles per decimeter cube. This is the concentration. And H2 they've already given me, it's 12.0 divided by 6.0. This is the concentration. And let me just calculate out those values to make it simpler for myself. 7.2 divided by 6.0 is 1.2. So this is 1.2 mole per decimeter cube, and this one is 12 divided by 6 is 2, obviously, so that's 2.0 moles per decimeter cube. And for NH3, I do not know the concentration. That's what they want me to find, so I'll just give it as X. Alright, so what is my Kc expression? Kc is NH3 squared. You have to use square brackets because square brackets, it's a convention in chemistry that square brackets represent concentration. Alright, N2, again I have N2, and then I have H2 cubed. Alright, so that's my Kc expression. Now let me substitute the values in. 6.0 into 10⁻⁻² is the Kc value that we have. NH3 is X, so I'm going to get X squared divided by N2, which is 1.2, and then multiply this by, or should I know my X's look a lot like multiplication signs. I'll work on that. H2 is 2.0 cubed. Alright, so then X squared, if I just cross multiply and just calculate this value out, 6.6 into 10⁻⁻² into 1.2 into 2 cubed becomes 0.576. Alright, so now my X is equals to the root of 0.576, and since concentrations are not really negative, so you do not take plus or minus root, you just take positive root. I mean, there's some complicated calculations where sometimes you do have to take plus or minus root, even for concentrations, because X is not representing a specific concentration. X, for example, 2 minus X is representing the concentration. So if you get 2 minus 1.2, that still works out, right? But that's not the case in A level chemistry. You won't need to do plus or minus square root. You just have to do positive square root all the time for concentrations. So let's do that. 0.576. That is approximately, they've given me 2 significant figures. So if I take it to 2 significant figures, I have approximately 0.76 moles per cubic decimeter. So that means my answer is B. Alright, done. That's the concentration of ammonia present in the equilibrium mixture at 500 kelvins. Next question, question number 11. Ammonia is made with a Haber process. The reactants are nitrogen and hydrogen. Alright, so what will increase the rate of the forward reaction? So they have shown that delta H is negative, which means the forward reaction is exothermic, the backward reaction is endothermic. So what will increase the rate of the forward reaction? They've talked about rate, they're not talking about yield. Remember in the previous question somewhere they asked about yield, which was this one, question number 2. No, they're not talking about rate. Alright, so what will increase the rate of the forward reaction? Adding argon to the mixture but keeping total volume constant. what will argon do? I mean, argon is not really even in this reaction, so if anything, it's acting as a catalyst, is it? But as I recall, the catalyst for this reaction is not argon, it's iron. Nevertheless, I'm really confused about what they're trying to say with this question, so I not eliminate A, but I do not think it's the right answer. Anyways, decreasing the temperature. Decreasing the temperature will not increase the rate of the reaction. It will increase the yield of ammonia, yes, because the reaction is exothermic, but it will not increase the rate because the particles will have less kinetic energy, so the rate is actually lower. So no, decreasing the temperature should not increase the rate. Increasing the total pressure by reducing the total volume at constant temperature. Well, if you're increasing the pressure, your particles, they are the frequency of collisions is going to increase. I mean, the particles are going, the collisions are more likely to happen because the particles are more like they're nearer to each other, right? Like they I mean to say, to reduce the volumes, the particles are closer to each other and more likely to collide successfully, right? So I think that C could be the right answer. Removing ammonia as it is made, but keeping the total volume of the mixture same. If you remove ammonia, well, the rate doesn't change. It's just that the yield of ammonia increases, yes, but the rate should not change. So that's wrong. Now, sometimes you just have to choose the best answer, the most correct answer. Adding argon to the mixture, making the total volume constant, that is really quite irrelevant in my opinion. I'm just going to cross it out, and so my answer is C. Increasing the total pressure by reducing the total volume at constant temperature, that's the one that makes the most sense. Now, question number 12. X is a group 2 metal. The carbonate of X, so I like to write down for any inorganic questions where they tell you a specific group of period, I like to write down on the side. So over here you have beryllium. My cousin actually taught me a way to remember this, which is Been Mohira Ka Sar Bada. So it's like it's a Urdu mnemonic, which is quite funny because my uncle's name is actually Mohira, so that's why she came up with it. And like, yeah, that's the way I always remember group 2. Been Mohira Ka Sar Bada. So yeah. Anyway. The carbonate of X decomposes when heated in a Bunsen flame to give carbon dioxide and a white solid residue as the only products. Very interesting. Just carbon dioxide and a white residue. The white solid residue, so I mean if a carbonate is decomposing, so for example let me just make a random XCO3, right? So XCO3 is decomposing when heated to give when heated to give you XO plus CO2, right? Because in group 2 you have X2 plus and O2 minus, so that means you get XO, right? So XO plus CO2, and if I balance this out, 1X, 1C, and 3, so 1, it's already balanced, bro. Anyways, and again, so X plus CO3, 2 minus, so this is also XCO3, right? That's the formula for group 2. Anyways, so carbon dioxide and white solid residue. The white solid residue is XO. This white solid residue is sparingly soluble in water. Even when large amounts of the solid residue are added to water, the pH of the saturated solution is less than that of lime water. So it must be less soluble in water than calcium, right? Because lime water is what is calcium hydroxide, right? So you have to remember that the solubility of the group 2 should I say hydroxides? Solubility of the group 2 hydroxides increases down the group, right? So magnesium is the least soluble if you're ignoring beryllium and radium. I don't know why, but for some reason we ignore beryllium and radium in AS and A2 as well. I don't know why, but we should not ignore them, but oh well. If you compare magnesium, calcium, strontium and barium, then magnesium has the least solubility in water, and magnesium hydroxide I mean, right? And whereas barium hydroxide is the most soluble in water, right? So if I look at it, so then if I have BaO, it will be the one that most readily is soluble in water, because the reason is basically like down group 2, if I compare MgO, BaO, like BaO has a very strong lattice, doesn't it? Because it has a greater lattice energy, which is something you learn in A2. But like magnesium, for example, is this size, and barium is this size, right? So barium is having a much lower charge density, and so it has a lower lattice enthalpy. So its lattice is am I doing this right? Wait, so it has a lower so its lattice is like decomposes much. I think I'm doing the opposite thing actually. Oh my god. Anyways, let's leave A2 things aside. But why am I even doing it for MgO? I should be doing it for MgOH twice. Nevertheless, the point is that the solubility increases down group, what's it called? Group 2, right? So my calcium, strontium, barium are out because MgO, it has a very, very strong lattice, doesn't it? Because Mg2 plus, O2 minus, and Mg has a very high charge density. Charge density is what is charge over size, and the charge density for magnesium is much, much greater than it is for barium, which has a bigger ion, but the same charge but a bigger size, which means the charge density is lower for barium, right? So it's just it's easier for barium to decompose, but magnesium, its lattice is much stronger, so it's harder for it to decompose in water. I suppose that's a simpler way to explain it. Yeah, so it's harder for magnesium to decompose in water because the Mg2 plus has so much charge density compared to Ba2 plus or whatever, right? And we're comparing it to CaOH twice, so the only option possible is magnesium anyways here, or beryllium, but beryllium is not an option, so yeah, magnesium. I think I'm giving too long explanations, very long explanations, but oh well, it's fine. Question number 13. Rat poison needs to be insoluble in rainwater, so means it's not aqueous. It'll have the solid written. It's not soluble in water basically, but soluble at the low pH of stomach contents, meaning it reacts with acid basically, you know. So what is a soluble barium compound used for rat poison? Well, if I look at barium, let me see which ones are actually aqueous first. So barium chloride is aqueous, so that cannot be an option. Barium hydroxide is also aqueous, so that is not an option because both of them can, you know, dissolve in water. And then you have barium sulfate and barium carbonate left over. Thing is, barium sulfate, it doesn't really react with acids much because it was formed from an acid, like it was, you know, H2SO4, right? Plus whatever, BaCl2 gives you BaSO4, and BaSO4 is, you know, yeah, so BaSO4. So the problem with that is that like BaSO4, so it doesn't really react with acids that much. It does react with, I think, hot concentrated H2SO4 because there's something involving H2SO4 minus, which I don't know exactly how it reacts with hot concentrated H2SO4, but it does. But with most acids, it doesn't really react. Even with hot concentrated HCl, it does not react. So this is wrong. Barium sulfate is not the answer. Barium carbonate is the answer because that's a test for carbonates, right? Carbonates do react with, because barium carbonate, like that's a base, right? So carbonates do react. All carbonates react with acids, and so that is obviously the answer because it's insoluble in water but soluble in acid, right? So that's the, you know, even in your practicals, you might have learned that like carbonate, the test for carbonates is usually you just react in acid with them, and then you get, if you get effervescence, then that means it's carbonate because you get hydrogen produced, right? So carbonate, barium carbonate is the suitable compound. Question number 14. Use of the data booklet is relevant to this question. Which of the elements, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and chlorine, which basically means period 3, and you're ignoring argon. Rest in peace argon, but we never mention it when you're talking about periodicity because I guess it's a noble gas, maybe that's why. But anyways, which of the elements has a lower first ionization energy than the preceding element in the periodic table, conducts electricity, and has a lower atomic radius than the preceding element in the periodic table? So you have to sort of tick all the boxes for this. So conducts electricity, I can already eliminate, like immediately eliminate phosphorus and sulfur because they are non-metals, so they're not really going to conduct electricity, are they? And so I only have magnesium and aluminium left. Now the question is, which has a lower first ionization energy? So aluminium has a lower first ionization energy than magnesium. Is that right or is that wrong? I mean, both of these are quite related actually. First and third statements are related, and for that I'll need to check the data booklet, which what are the radii of aluminium and magnesium. So let me do that. Where are they even written? Oh my god. Yeah, here they are. So aluminium, its atomic radius is 0.143 nanometers, and for magnesium it is 0.160 nanometers. So which has the lower atomic radius? That is aluminium. And since it has the lower atomic radius, so that means that it because you know the general trend in a period is that since your general trend in a period is that like your number of valence shell electrons are increasing, right? So then your atomic radius gets smaller and smaller and smaller, right? So what does that mean? That means that your nuclear force of attraction on the valence electrons gets stronger as you go right, like you go from right to left to right in the period, and so your ionization energy actually increases, right? So that's the thing. But then, so the lower atomic radius is for aluminium. You don't even need a data booklet for that. But then the problem comes with Al plus and Mg plus when you're considering the lower first ionization energy. Does magnesium have the lower first ionization energy, or you don't actually need a data booklet for this. I don't know why I did that, but it's been a long time since I've studied AS, is my excuse. But lower first ionization energy, that is true, because if you write down the configuration of magnesium, I hope I haven't said anything wrong. If I've said anything wrong, kindly correct me in the comments, alright, because that would be of benefit to the other people. So magnesium has 12 electrons in total, and aluminium has 39 electrons, right? So if I draw out the configuration for magnesium, then it's 1s2, 2s2, 2p, 2p4. So that's how many electrons are left for me. 12 minus 4 is 8. So 2p6 and then 3s2, right? That is the configuration for magnesium. And then for aluminium, what do you have? You have 1s2, 2s2, 2p6, 3s2, 3p1, which is aluminium. So aluminium atom has a slightly greater atomic radius. Well, I wouldn't want to say it has a slightly greater atomic radius, because like I just showed you from the periodic table, so that is why we need the data booklet actually, that it has a lower atomic radius, right? Because it's it has a lower atomic radius than magnesium. I will quote the values again: 0.143, 0.160. So it has a lower atomic radius, yes, but you have another subshell as well in aluminium, and the subshell means that you're like you have more shielding in aluminium actually. It's slightly greater atomic radius in that sense, but actually according to the data booklet it has a lower atomic radius, but that is true. But it has more shielding, because over here we have shielding from all of these, right, for magnesium, but for aluminium we have shielding from the 3s2 as well. For 3p1 you have shielding from 3s2, because lower subshells can shield the higher subshells. So that means that it's the nuclear force of attraction on the valence electron for aluminium, the outermost valence electron, will be lower, because lower, it will be lower nuclear force of attraction because it has more shielding, right? The outermost electron is more shielded, which means that if it has a lesser nuclear force of attraction to the nucleus, the outermost electron, then that means it has a lower first ionization energy, right? So that means that my answer must be aluminium. And I know that was a very long-winded explanation, and I hope that wasn't too confusing, but yeah, basically the answer is A. And yeah, this is it. Next question. The melting points of the period 3 elements sodium to aluminium are shown in the table. Which factor explains the increase in melting points from sodium to aluminium? So the melting points are increasing from sodium to aluminium, and the explanation is that they exist as metallic lattices, don't they? So that means you have delocalized electrons in the lattices, so you have like Na plus and then an electron, each Na has one electron to it, and so they exist in lattices, and like from Na plus to Mg2 plus to Al3 plus, your number of delocalized electrons, or the number of electrons you have in the conductivity band, that increases, right? So that's why your melting point increases, because if you have a greater sea of electrons and an ion of greater charge density, then you're going to have a stronger metallic lattice, aren't you? So that's the reason. And so which factor explains the increase in melting point from sodium to aluminium? The changes in first ionization energy from sodium to aluminium. The increase in electronegativity from sodium to aluminium. I do not want to talk about ionization energy or electronegativity here. The increase in the AR of the elements from sodium to aluminium. Not really. I mean, guess the size. I mean, what are they even trying to say? I do not know. I mean, am I going to cross out all 4 options or what? The increase in the number of outer electrons in each atom from sodium to aluminum. That's what I said, right? The number of delocalized electrons, or the increase in the number of outer electrons increases, and so yeah, because they exist in metallic lattices, right? So yeah, that's the answer. Next question. X is the oxide of a period 3 element. Again, I like to write down what are the period 3 elements. For questions like this, I just like to write things down. So sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Alright, so it's the oxide of a period 3 element, and X reacts with water to give an acidic solution. If it reacts with water to give an acidic solution, well, Na2O will not give you an acidic solution, MgO will not give you an acidic solution, Al2O3 could give you an acidic solution. So I can already cross out B, and SO3 could give you an acidic solution, yes. SiO2 plus H2O. Is that even a reaction? I do not think it will react with water, am I right? It reacts with NaOH, but it does not react with water, I think. So I can cross Si as well out. And P4O10 is an option, which is possible to give an acidic solution. Chlorine I can cross out because it's not one of the options. And what I don't even know a period 3. I don't even know. I mean, whatever. But Ar, again, like it's a noble gas, I can cross it out. So my aluminium, phosphorus, and sulfur are the ones that are left. Now a solution is prepared by reacting 0.100 grams of X with excess water. So this means this is the limiting factor, right? The solution was neutralized by exactly 25 cubic centimeters of 0.1 mole per cubic decimeter sodium hydroxide solution. Now, what does that mean? So let me firstly find out how many moles of NaOH this is. So NaOH is equals to CV, right? CV. So it will be 25.0, and to convert from CM3 to DM3 multiplied by 10 to the power minus 3 into 0.100 mole per cubic decimeter. So that becomes 25 into 10 to the power minus 3 into 0.1. So that is 0.00250 moles of NaOH. Alright, so that's my first thing that I'm going to do. Next, I'll just let me think about this. What's a good way to approach this question? How about I just write down the equations for each of them? So if I start out with which one to start out with? Actually, I'm going to cross out Al2O3 as well, because it itself with water will not give you an acidic solution, right? If it reacts with a base, it gives you an acidic reaction. If it reacts with an acid, it gives you an basic reaction. So I'll cross out that as well. So now I only have 2 left, P4O10 and SO3. And anyways, Al2O3 doesn't really, Al2O3 and MgO both, they are very, very insoluble in water because they have such strong ionic lattices, right? Or actually, Al2O3 has an ionic with a bit of covalent character lattice, but the point is that they're both quite insoluble in water, so I can cross them out. So let's start with P4O10. So P4O10 plus H2O will give me what? It will give me phosphoric acid, am I right? H3PO4, and that should be it. But I just have to balance the equation, obviously. So I have 4 P's here, so 4 P's, 4 is at 12, so 6 H2O, is that balanced? 10, 6, 16, and 4 is 16, yes, it's balanced. So following this, my other reaction will be H3PO4 plus NaOH gives me it's PO4 3 minus, right? So PO4 3 minus, when it comes to Na, this will become Na3PO4. So that should be my salt that is formed is Na3PO4, and I get water as well because with an acid reactant in the base, right? So water. And let me just balance this out. So I'll put 3 here. And what else? How should I balance this, bro? Na3PO4 and 3 there, 3 there, 3 hydrogens, that's 6 hydrogens in total. So I'll make this 3, 3, 4, 5, 6, 7, 7 oxygens, 4, 5, 6, 7, 7 oxygens, balanced. Alright. So those are my 2 reactions, and we have 0.100 moles of this, which means this is a 3:1 mole ratio, right? So how many of H3PO4 should I have? I should have 0.1 divided by 3 moles of that, which is 0.03 moles, where 3 is recurring. So that's the number of moles I have. So if I write this down here as well, I'm just going backwards in my calculations. Okay, so this is 0.03 moles. So if I want to find the P4O10, so if my P4O10, I have 4 moles of H3PO4 is to 1 mole of P4O10, right? So that means if I want to find the number of moles of P4O10, that should be 0.03 divided by 4, right? So 0.03 recurring, I mean, so I'm just going to use my calculator value, divide that by 4. I get 0.0083. This dot means recurring, by the way, moles, alright? So that's the number of moles I get. Now, to find out if this is correct or not, what I should do is they've given me 0.100 grams of X, right? So I'll find the moles of P410 using this. So N equals M over MR, so 0.100 divided by the MR of P410, which is, I'll just use periodic table. So phosphorus has an MR of 31, so AR of 31, so 31 times 4 because there are 4 phosphorus atoms, 124 plus 16 because that's the AR of oxygen times 10 oxygen atoms, so that's 284. So 0.100 over 284 gives me 0.00035 moles approximately, and there's a big difference between 0.0083 and 0.00035, don't you think? So that means that probably C is not my answer either, which means D is my answer. But just to verify, I will do the same thing with SO3. Alright, so let me erase this beautiful mess and do the same thing with SO3. Hopefully I'll get the same answer, but if not, then I'll have to think of another way to do this question. And yeah, let's see. So SO3 plus H2O gives me H2SO4. It's an acid. So acid plus base will again give me salt plus water. So H2SO4 plus NaOH gives me Na2SO4, or you can say NaHSO4 I suppose as well, but I'm going to do Na2SO4 plus H2O, so to balance this I'll put 2 here, plus 2Na, 2Na, and then I have already balanced the SO4 part, now I just need to balance the oxygens and the waters, so I can make this 2 2s are 4, 2, right, balanced, okay? Now, again, I calculated this before, but I erased it, so let me just calculate it out again in my calculator. We had 0.002 0.0025 moles of this, right? Leave the 0, I don't keep proceeding for the figures here. So then how many moles of H2SO4 I have? I have half of that. So that is 0.00125 moles of H2SO4. I write that down over here as well. Then the SO3 is to H2SO4, that is 1:1 molar ratio, so that means this is also 0.00125 moles according to whether when I go backwards in my calculation using concentration, the moles of sodium hydroxide, but if I do it using what this thing they've given me, so then the moles should be 0.100 divided by the MR of SO3, which is 32.1 plus 16 times 3, which is 80.1. So 0.1 over 80.1 gives me, ooh, look at that. I get, I write it over here, I get 0.001248, which is approximately, oh my god, my beautiful handwriting, 1248. Okay, so I will approximate that to 0.00125. That's much closer than we had gotten from P4O10, right? So that means this is the right answer. D is the right answer, and that is the explanation behind it as well. So, alright, now next question, 17. Which statement about bromine is correct? Bromine is insoluble in non-polar solvents, but bromine itself is a non-polar molecule, so it should be soluble in non-polar solvents, shouldn't it? So this is wrong immediately because a non-polar molecule should be soluble in non-polar solvents. And then bromine vapor is more dense than air. Well, air normally we talk about it as consisting of nitrogen and oxygen and other things like argon and carbon dioxide. If you check what's the bromine vapor's MR, that is one bromine atom has an AR of 79.9, so 79.9 into 2 would be 159.8. So 159.8, and if I check for this stuff, if I do to N2 plus O2 plus CO2, N2 is going to have an MR of 14 into 2, that's 28. Oxygen will have 16 into 2, that is 32, and then CO2 will have 12 plus 16 times 2, 32, so that is 104. So 104, and the small MRs of argon and stuff like that, so that's 104, which is obviously less than 159.8. And I feel like, yes, it's quite true that bromine vapor is more dense than air. I believe that you should know that by now, like as chemistry intuition, I feel. Okay, and so yeah, I feel like B is the correct option, but let's check the other choices. Bromine will not vaporize significantly under normal conditions. Well, as we mentioned, bromine is a non-polar molecule, right, which means it has a low boiling point, especially if you consider that water, which has hydrogen bonding, it has a boiling point of 100 degrees Celsius, right? Now if I check what is the boiling point of Pr2, so that is or should I say bromine? I'll make it bromine. Oh my god. That's 59 degrees Celsius, which is much lower than 100 degrees Celsius, is it not? So it has a 59 degrees Celsius. So why would it not vaporize significantly under normal conditions? I don't know why. And evaporation will still happen, won't it? If you're not even talking about boiling. So that's wrong. Gaseous bromine is purple. No, it's like reddish brown. Gaseous iodine, on the other hand, is purple, but we're not, this is wrong. Gaseous bromine is not purple. So the answer is B. Bromine vapor is more dense than air, which is why we collect it by downward delivery. Am I right? Yeah. Okay. Now next question number 18. The addition of aqueous silver nitrate to aqueous barium chloride produces white precipitate. So if I just write down the reaction, AgNO3 plus BaCl2 gives me, what does it give me? AgCl plus BaNO3, right? And nitrates are obviously always soluble. This is soluble, and this is soluble as well, but then this is a solid. If we just balance the equation, although we don't need to, but I don't want to balance this, but oh sorry, this should be BaNO3 twice. That's the mistake, because Ba2 plus NO3 minus, that becomes BaNO3 twice. That's why my balancing was so weird. And it's 2 AgCl, right? Now it's balanced. Okay. So that gives me a white precipitate, which is AgCl, and which dissolves in excess dilute aqueous ammonia to form a colorless solution, which is a diamine complex, right? So when you have AgCl plus NH3, you get AgNH3 twice Cl, which is, or you can say this as plus and Cl minus, or you can write it separately as well. I suppose that's a better way to do it. Cl minus. So the charges, both charges cancel out, plus minus 0. Here also you have 0 charge, so you'll have a balanced chemical equation. Now it's balanced actually. Yeah, now it's balanced. So this is your diamine complex which forms, right? And the addition of excess dilute nitric acid, which is HNO3, to the colorless solution produces a white precipitate Z. So if I add HNO3 to this, then I'm adding H plus and NO3 minus, right? So if I add H plus, what does that mean? That this is NH3, right? So it will react with the NH3, and so I will get NH4 plus from there, because H plus and NH3 will react to give you NH4 plus, and then I have Ag plus and Cl minus, which reform to give me AgCl solid again. So like you get the same thing here you get the same thing, AgCl solid, and so the white precipitate Z is AgCl solid. It's not BaNO3. I mean, it's quite obvious common sense as well. You don't even need to do all these equation things, because paper 1, right? So you have to be fast with paper 1 setting. So NH4 NO3 is soluble, BaNO3 twice soluble, all nitrates are soluble, BaCl2 again I showed you over here is soluble, and AgCl is the only one that's a precipitate. So then the answer is A. That's it. Done. And question number 19. Element X forms polyethylene oxide Y. Y can be further oxidized to Z. Two students made the following statements. Student P, the molecule of Y contains lone pair of electrons. Student Q, lone pairs of electrons. That's curious. Student Q, the oxidation number of X increases by 1 from Y to Z. X could be carbon or nitrogen or sulfur. Which students made a correct statement? Well, let me draw it out. How about, so it could be carbon or nitrogen or sulfur. So then if I have a polyethylene oxide Y, right? So C, for example, I'm starting with carbon. So carbon plus oxygen gives me carbon monoxide firstly, which is further oxidized to carbon dioxide. Alright, that's my first one. Then second, if I consider nitrogen, I have N2 plus O2 gives me again nitrogen monoxide. So let me get 1 by 2 N2 plus 1 by 2 O2, and then NO plus half O2 gives me NO2, right? So that's my second one. And then if I consider sulfur finally, I'm just going to take it as S, but if you want you could take S8 I suppose, but S just makes things simpler. Alright, S plus O2, in this case O2 gives me SO2, and then SO2 plus 1 by 2 O2 gives me SO3. Alright, the molecule of Y, so let me just label X, Y, Z as well. This is X, this is Y, this is Y, this is Z, this is X, this is Y, this is Y, this is Z, this is X, this is Y, this is Y, and this is Z. Alright, so the molecule of Y contains lone pairs of electrons. Does CO contain lone pairs of electrons? Let me see. CO, carbon is attached to 3. Well, actually there's one that's not like this. There's one that's not the structure of carbon monoxide. Carbon monoxide has one dative covalent bond as well, but I forgot whether it's from carbon to oxygen or oxygen to carbon. I'm going to take it as, let me just see if this gives me complete octets. So if I take the dative bond from oxygen to carbon, so 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, that's 8, and it has 6 different valence shells, 4 different valence shells, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that is the structure of carbon monoxide, and it's a complete octet and all. So it contains lone pairs of electrons. Well, it does, 2 lone pairs of electrons. So for carbon, the first statement is true. I need 3 ticks. Or do I need? Could be carbon or nitrogen or sulfur. So even if one of them satisfies the condition, I suppose it works, doesn't it? Yeah, so I suppose I don't need to do it for nitrogen monoxide and SO2, but if any of them also satisfy it, that would be fine. But it's not carbon or nitrogen or sulfur. Like I don't know if I'll check later, but for now I'll check Q first and see if that works out. So I have oxidation number of X increases by 1 from Y to Z. So Y, I have this as, this is minus 2, this means this must be plus 2, because overall charge of a compound should be 0, right? So minus 2 plus 2 becomes 0. So that's plus 2, and over here we have minus 2 times 2, that becomes minus 4 for oxygen in total, and then for carbon it will become plus 4. Plus 2 to plus 4, that is increasing by 2. So firstly I have got wrong, but let me check for the others. So N, I have again over here I have N as plus 2, and Z I have again as plus 4, so that's again wrong. But then let me check sulfur finally. This is minus 2 times 2 becomes minus 4, so this becomes plus 4, and oxygen here is again minus 2, and if you have 3 oxygen atoms, so times 3 becomes minus 6 overall charge, and so minus 6 to balance that you have plus 6, so again it's increasing by 2. So by on all of them it's increasing by 2, which means I have 3 wrong, which means student Q is not right at all, which means my only neither P nor Q. Again, neither P nor Q, I do not want to say that's the right answer either, because X could be carbon or nitrogen or sulfur, so my answer is P only. But let me check for nitrogen monoxide, I suppose, as well. What's the structure of nitrogen monoxide actually? I don't even know. Let me just check it. Nitrogen monoxide structure, right? That's the structure of nitrogen monoxide, pretty cool. Nitric oxide, that's how they label it. So nitrogen monoxide or nitric oxide. So let me just, so it has a double bond actually, very interesting. So it's a double bond, and well, there's one lone pair. This is a lone pair that's just 1 electron, and it has 5 electrons, 1, 2, 3, 4, 5, and then over here you have 2 electrons, and then 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So sort of like a free radical substitution. I don't know, but it's not balanced at the very least. Anyways, that's the structure of nitric oxide, which I always get confused about actually. But nevertheless, that's not the point here. The point is that it does have lone pairs. So that statement is correct. And then the molecule of Y contains lone pair of oxygen. Now let me check for SO2 as well, which obviously I'm sure of it that it does contain lone pair C, because it has bonded to 2 oxygen atoms with double bonds, and so 1, 2, 3, 4, and then it has to have 6 electrons in its outer shell, so that's 1 lone pair. And then oxygen is bonded like this, so then it has 2 lone pairs of electrons, actually 1, 2, 3, 4, 5, 6, so that's 2 more lone pairs, and then I have 2 more lone pairs here, don't I? So then that means that for P I have 3 ticks, and for Q I have 3 crosses, which means my answer must be A. And yeah. Alright, next question. How many, let me erase this so I have more space for the other question. Next question. Now we're at the organic chemistry portion, which is amazing. I love organic. I love inorganic and organic and physical, actually. All of them are so beautiful. But yeah, mathematically deriving chemistry is my favorite, so then physical is my favorite. Anyways, how many isomeric esters have the formula C4H8O2 esters? Okay, so let us start with methanoic acid. I like drawing skeletal formulas, okay, so I'll draw skeletal version. So I'm starting out with methanoic acid, which means I will need propanol. So I have 1 carbon atom there, and 1, 2, 3 carbon atoms there, so I have 4 in total, and that is one of them. That's number 1. I'll count them later, actually, okay? Then what else can I have? I can have this same thing, but with a branch. So I make 1, 2 here, and then a branch over there. So that gives me 2 from methanoic acid. Then if I make my methanoic acid 2-chained, if I make the acid having 2 carbon atoms, so 1, 2 carbon atoms, and then I have 2 carbon atoms for my alcohol part as well. So carboxylic acid part has 2 carbon atoms, and alcohol part has 2 carbon atoms as well. So I get this thing. So that's 1, 2, 3, 4, and I cannot have any other isomers from that. Then if I make my carboxylic acid have 3 atoms, so I have the COO bond, and then I have 1 carbon atom there, 2, 3, 1, 2, 3 carbon atoms, and then that means my alcohol will have just 1 atom. So that's that way. And can I have any branches from this? I cannot, because you cannot attach here many things like that. So that means I have these are the only ones I can come up with, which means I have 4 esters. If you can think of any others, that would be great, but I'm only coming up with 4. And I think that's the answer, because I really cannot think of any others. And for these type of questions, you should just be methodical and go step by step. Like, don't randomly jump from 1 carbon atom carboxylic acid to 3 carbon atom carboxylic acid. Go step by step. 1, 2, 3, step by step, methodically. Next question. A new jet fuel has been produced that is a mixture of different structural isomers of compound Q. Which skeletal formula represents the structural isomer of Q? Alright, let's see. So over here my parent carbon chain has how many atoms? 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, 9 carbon atoms, and I have branches on the 2nd, 3rd, 5th, 7th, 8th. Alright, now let's look at this one. I have 1, 2, 3, 4, 5, 6, 7, 8. That's already suspicious that parent carbon chain has 9 atoms. Then I have branches on the 2nd, 3rd, 5th, 7th, and 8th. So it's literally the same as Q. Like, it's not a structural isomer of Q. It's the same compound Q. So like I mean to say it is obviously it's the same compound Q, but like it's not an isomer of it, is my point. So that's wrong immediately. And then let me look at this one. 1, 2, and how many atoms does it have in total? So 9, and then 10, 11, 12, 13, 14. So it has 14 atoms in total. This one also has 14 atoms. 1, 2, or should I start from? Doesn't matter. 3, 4, 5, 6, 7, 8. 8 atoms in the total chain. That's good. And then a branch is on the 5th one, and ethyl branch on the 3rd one, and a branch on the 4th one, again ethyl. And how many atoms does it have in total? It has 8, 9, 10, 11, 12. That is suspicious. Wait, let me just count them again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, 13. Let me just count them again. 8, 9, 10, 11, 12, 13. Yeah, it has 13 atoms, so that means it must not be the right answer because it has the same number of carbon atoms in it. And let's go to this one. 1, 2, 3. Or is it not a good idea to do that? I don't know. Where should I start counting from? This is so annoying. I'm going to just start from here. 1, 2, 3, 4, 5, 6, 7. So it has 7 atoms in its longest chain. A branch on the 5th one, a branch on the 4th one, a branch on the 6th one, a weird branch on the 3rd one, and a branch on the 2nd one. 7 and then 8, 9, 10, 11, 12, 13, 14. 14 carbon atoms in total, am I right? Yeah, so 14 carbon atoms. So this could be likely because it's not the same compound and it has the same number of carbon atoms. I just check the last one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Branch on the 8th one, branch on the 7th one, branch on the 5th one, branch on the 3rd one, branch on the 2nd one. Again, the same compound, and that means it probably has the same number of carbon atoms as well, 14. So this cannot be the answer as well. So the only option left is C, because these 3 are eliminated, A, B, and D. So that means C is my answer. Great. So next question. Crude oil is a mixture of many hydrocarbons ranging in size from 1 to 40 carbon atoms per molecule. Oh god, that's a very big number. I mean, 1 to 40 is a lot. The alkanes in crude oil can be separated because they have different boiling points, right? So you separate them based on the strength of their van der Waals forces. Table below shows the boiling points of some alkanes, and they're alkanes, so they don't have any other IMFs, intermolecular forces than temporary dipole-induced dipole forces. They do not have permanent dipole. They do not have hydrogen bonding. So what is the correct explanation for the difference in the boiling points of the 3 isomers of MR72? So you're talking about pentane and about 2-methylbutane and about dimethylpropane, right? So branching is dependent upon the length of the carbon chain only. Well, no, not always. I mean, in this case perhaps, but not always. Depends on like what IMF forces you have. So I suppose that's not the right answer. But if you're talking about this question, then I suppose it's right. Increased branching on a carbon chain increases the boiling point. Well, let me see. Pentane is like this. 2-methylbutane is drawn like this, and dimethylpropane is drawn like this, right? So increased branching on a carbon chain increases the boiling point. Well, dimethylpropane has the most branching, but it has the lowest boiling point, so no. Increased branching reduces the strength of the intermolecular hydrogen. You don't even have hydrogen bonding here, bro. Increased branching reduces the strength of the intermolecular van der Waals forces. That is right, because the more branches you have, the less your molecule's surface area becomes, because this is a longer molecule. I shouldn't talk about length, I should talk about the surface area exactly, but basically branches reduce the contact points, so to speak, of your molecule, and so you have a lower boiling point when you have branches. So that should be the right answer, so I'm going to eliminate A as well, because boiling is not dependent upon the length of the carbon chain only, right? So increased branching reduces the strength of the intermolecular van der Waals forces, which is what you're seeing here, that you have less branches going from pentane to you have more branches going from pentane to 2-methylbutane to dimethylpropane, even though they're the same MR molecule, right? And so the boiling point reduces, right? So the answer is D. Question number 23 now. Compound Q contains 3 double bonds per molecule. Great. You can see that X, Y, and Z. Which bond X or Y will be ruptured by hot concentrated acidified KMNO4, and how many lone pairs of electrons are present in one molecule of Q? Well, hot concentrated acidified KMNO4 is usually for the oxidation of alkenes, right? And CO anyways, it's like a ketone group, so it won't be further oxidized. Ketones cannot be further oxidized, right? So that means X is the one that is ruptured. So you say that that's your answer, X firstly, and the number of lone pair of electrons present in one molecule of Q. Let's see. How many lone pairs of electrons are present? Well, oh no, what happened? My screen. Okay, anyways, C is bonded always in organic chemistry. C is bonded to 4 electrons usually. So I can disregard this, disregard this, disregard this, disregard this, disregard this, disregard this. I can discard everything except the oxygens. Oxygen here is bonded to two things. That means it has 2 lone pairs of electrons, because oxygen has 6 valence electrons, right? So if it's bonded to 2 things, then that means you have 4 electrons left, which means it has 2 lone pairs. 2 lone pairs here, and again here is bonded by 2 bonds, so that means it has 2 lone pairs. And over here again it has 2 lone pairs. So that's 1, 2, 3, 4, 5, 6. 6 number of lone pairs. So that means my answer is, where there are 2 ticks, that is B. Okay? So yeah. reaction with NaOH. Just wait a second. Things have gone. Yeah, okay. Anyways, which compound undergoes an SN1 substitution reaction with NaOH? So SN1 means what? SN1 means we're talking about tertiary halogenoalkanes. Am I right? SN1 is the two-step reaction which is undergone by tertiary halogenoalkanes because they form more stable carbocations because they have 3 R groups, right? So that means it takes they don't spontaneously have nucleophilic substitution. They form a stable carbocation, which means they need to go through 2 steps instead of just 1 simultaneous step. So an intermediate is formed basically, and a reaction with NaOH aqueous. So I need a tertiary halogenoalkane ideally, or let's see, CH3CH2Br, that is not a tertiary, that's a primary haloalkane, so I can cross that out. CH3 twice CH2, I cannot really see it clearly. Let me just draw it out to make it easier for me to see whether it's tertiary or not. CH3, and then this is bonded to CH2I. So this iodine, this is bonded to this carbon, and that carbon is bonded to 1, right? Am I doing that right? Or should I consider this Ci bond? Well, no, I should consider the CH3 thrice Br, right? CBr. Yeah, so that is a tertiary halogenoalkane. This is a primary halogenoalkane because this carbon is attached to 1 carbon atom directly, right? So this is a primary one, so I can cross that out as well. I don't know why I was so sometimes I just get confused, and that's normal actually. Anyways, if I look at this chlorine, it's attached to this carbon directly, and this carbon is attached to 3 other carbons directly, this carbon, so that means that this is a tertiary halogenoalkane, which means it must be my answer. CH2 CHCl, if I look at that, I don't even know what that is, bro. CHCl, I mean that's attached to this carbon, which is attached to 1 carbon atom directly. It's not even, it's not a tertiary or so whatever. It's only attached to 1, so it's not my answer. It's not a tertiary halogenoalkane. So my answer is C. Okay, great. Next. If the starting material is iodoethane, which sequence of reactions will produce propanoic acid as the main final product in good yield? Alright, so I have iodoethane, which is, how should I draw it? So I have ethane, and this ethane is also attached to an iodine molecule. All the other ones are a hydrogen, but this is an iodine. We have an iodine, alright? So which sequence of reactions will produce, you're starting from iodoethane and you want to get to propanoic acid, alright? So that's what you're trying to do. Now, which will produce propanoic acid as the main product in good yield? So iodoethane, it has 2 carbon atoms, and propanoic acid, so this should be how you draw it actually, right? So then you have 3 carbon atoms in propanoic acid, which means when you look at that means you need to add CN, because CN is the one that adds carbon, right? So if I have add NaOH acid, then blah 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 blah, that's immediately wrong. Add NaOH blah 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 blah, you don't have any mention of CN, that's already out. Now these 2, they have mention of CN, so I'm keeping them there. And heat with HCN in ethanol, isolate the organic product, add H2SO4. Now that could be right, but the problem is HCN in ethanol is not for haloalkanes, that's for aldehydes and ketones, right? I mean, both of them, I think, right? Aldehydes and ketones, or is it? Yeah, I think so. Both aldehydes. I should really revise my organic chemistry, but yes, HCN in ethanol is not the one you use to add CN to haloalkanes. You use KCN with ethanol, right? So your answer is D. Basically, that's immediately process of elimination. You use D. Your answer is D. And if you want to see that, so then if I add KCN, ethanolic KCN to this, I will get this. Sorry, in fact, if I don't make it like that, I should make it like I have these 2, and then I have one cyanide here, which is attached by a triple bond. So 1, 2, 3. In fact, no. Am I making this right? Or should I just not bother? Well, that's obviously wrong. Yeah. So this is my structure. Or should I actually, maybe it would be better if I represent it like this. So make it a bit more tilted perhaps. So CN. This point is 1, 2, 3 carbon atoms, and then it's CN. The CN is there, right? So you get that, and in fact, I don't know. I personally want to just draw it like that, so I'm going to keep it like this. Okay. And then this one, when you add H2SO4 aqueous, you're doing acid hydrolysis, aren't you? Because you're adding H2SO4 aqueous, and so that becomes the cyanide group will hydrolyze to make your COOH, obviously. Okay, so that is what happens. And since H2SO4 is acid hydrolysis, so it won't become ONA, it will remain as OH. And so your answer is D. Right? Next question. Which compound cannot be oxidized by acidified potassium dichromate solution? So K2Cr2O7H+, but does react with sodium metal. So it cannot be oxidized by acidified potassium dichromate 6 solution, which is usually the one that we use for alcohols, right? So but does react with sodium metal means it's still an alcohol, or could be a carboxylic acid, could include one of those. So if you look at let me try from the top. So I have CH3 thrice COH. So if I just draw that out, CH3, then I have an OH. So that is a tertiary alcohol, which means it cannot be oxidized, because tertiary alcohols are not able to be oxidized, right? Like, how would you make this into a double bond? Like, carbon cannot have 5 bonds. It's impossible for tertiary alcohol to really be oxidized and stuff. It doesn't have any it doesn't have any hydrogen CH or anything, right? So it's really hard it's impossible for tertiary alcohols to be hydrolyzed. So this meets the first condition. But does react with sodium metal? It does react with sodium metal because it has OH. So my answer is immediately A. But let's check the other options. CH3CO, CH2CH3, again, because it's a ketone cannot be oxidized further. For the same reason, like how many bonds it forms, so ketone cannot be oxidized further. And because oxidation is loss of hydrogen or gain of oxygen, right? So that cannot take place for a tertiary alcohol or ketone. But it does, so yes, it cannot be oxidized by acidified potassium dichromate solution, but it does not react with sodium metal because it's not OH or COOH, so that's wrong. CO cannot react with sodium metal. And then you have this one, which reacts with sodium metal, but it's not a tertiary haloalkane, it's a primary alcohol, so it is wrong as well. Then you have this one, which is secondary. So if you just make it like this, this carbon is attached to 2 carbon atoms directly, right? So that means it's a secondary alcohol, which means it can be oxidized further into a ketone, actually, and it does react with sodium metal, so it can be oxidized, which means it's not the answer. So your answer is A. Done. Next question. Butane 2-ol can be made by reducing X with H2Ni. So X with H2Ni, which is a very strong reducing agent. It's not a very selective reducing agent. It reduces a lot of things. I think most things it can reduce. I'm not sure about what exactly the things that hydrogen with nickel catalyst can reduce, but it's a very, very strong reducing agent. Okay. So this is what you have. Butane 2-ol. This is how to draw butane 2-ol 4 carbon atoms, and then a branch of the second one, which has OH. Okay, and now butane 2-ol can be dehydrated to form Y and Z, which are structural isomers of each other. So dehydration means you have formed an alkene. So you have formed this, and you have formed this and this, right? Because when you dehydrate it, you can form a double bond here, or you can form a double bond here, right? So that's why. Form a double bond here, then this is what you get. If you form a double bond in the middle, then it's like this, or you can get cis trans or cis. And so which row is correct? X is an aldehyde or a ketone. Well, since X, this could be formed from this compound, right? So if we have this, then this could be reduced to that. So X must be a ketone, definitely, because it's in the middle. Then you have the OH. And then cis-trans isomerism is shown by both Y and Z. Y and Z are structural isomers of each other, which means, for example, this is Y and this is Z. So cis-trans isomerism is shown by both Y and Z. That's wrong. It's shown by only Z in my example, which means only one of Y and Z. And so this is like, basically you could say Z1 and Z2. Right? So my answer is D. Okay. Question number 28. Tollens reagent agent can be used to help identify compounds P, Q, and R. Which compounds form a silver precipitate on warming with Tollens reagent? So Tollens reagent is a test for aldehydes, is it not? So it's like the OH group, basically that's what we're trying to find. So which one have aldehyde groups? This is a ketone, so that's wrong. This is an aldehyde because it has COH and an R group there. So P can form a silver precipitate. Q only is out basically, and R only is also out because P has to be in the answer. Now P and Q is also out because Q will not form a precipitate, so the answer is B. R, if we take it out, it will not form a silver precipitate because it doesn't even have a CO at all. So that's stupid. Anyways, the answer is B. Alright. Next question. Sorbitol is a naturally occurring compound with sweet taste. Awesome. I've actually read the name sorbitol on some food packaging or sweets packaging. I've read the name before. It is often used as a substitute for sucrose by the food industry. Often. See, that's what I said. I've read the name before on food packaging. How many chiral centers are present in sorbitol? So for a chiral center, you have to have two different groups. If you look at this carbon, usually in AS and A2 we talk about chiral centers with the center being carbon, but you could have other centers as well. But at least in AS and A2 you have carbon as the chiral center. I don't know about A2 because I haven't studied A2 fully, but AS I'm sure about. So you have two of the same groups here, so that means this is not chiral. You have four different groups for. This is a chiral carbon because it has four different groups attached to this one group, second group, third group, fourth group. This is a chiral carbon because one group, two group, three group, four group, all of them are different. This is also a chiral carbon because one group, two group, three group, four group, all of them are different. And this is also a chiral carbon atom because one group, two group, three group, four group, all of them are different, right? So I have four chiral carbon atoms, and that again it has two of the same group, so it's not chiral. So my answer is B, right? Which compound produces butane 2-ol and ethanoic acid on hydrolysis? So I need butane 2-ol and ethanoic acid. Okay, so let us see which compound. I need to have a compound which has 1, 2, 3, 4, 5, 6 carbon atoms. So let me just eliminate that first. 1, 2, 3, 4, 5. I have 5 in this, so that's wrong immediately. 2, 3, 4, 5. Right? That's immediately wrong. Then 1, 2, 3, 4, 5, 6. That could be an option till now. 1, 2, 3, 4, 5. So that could be an option. 1, 2, 3, 4, 5, 6, 7. That is 7. So that's wrong as well. 1, 2, 3, 4, 5, 6, 7. Okay, so now my only options left are B and C. So let's see. So if I just draw this out, CH3COO. So that's CH3COO. And then I have 1, 2, 3 in the parent chain. So there's 1, 2, 3 carbon atoms, and then I have a branch on this carbon atom, right? So that's how to draw this molecule. And if I hydrolyze this, I get ethanoic acid. Firstly, yes, and then the alcohol I get is this, which 1, 2, 3, 4, and that's not the proper way of drawing it. Obviously, if you can draw it, a better way of drawing it would be this way. But my point is that on the second carbon atom, I have my OH group, which is what happens in butane 2-ol, and the main chain has 4 carbon atoms just like butane 2-ol. So that means my answer is probably B because I get ethanoic acid and butane 2-ol. So my answer is B. But let me check this one as well. So CH3CH, CH3CO. For this one, I think it's better if I draw it like this because I don't know. The chain, that's why CH2, CH3. Doesn't matter whether if you're more comfortable with skeletal formulas or more comfortable with these ones, it's better. It's just that skeletal formulas are more quicker, convenient, so it's better if you get used to doing them. But yeah, so I get CH3, CH, CH3, COOH, and I get CH3, CH2, OH. So I get butane 1-ol, and I get what is that? 1, 2, 3 OH, CH3. So that's 1, 2, 3. That is ethanoic acid with a branch as well. I really I don't want to name it, bro. 2-methyl ethanoic acid, whatever. But the point is that you don't get ethanoic acid and butane 2-ol. Alright, so then that is not the answer as well, and my answer is B. Great. And now the next question. Which statements about orbitals are correct. So krypton, if I look at it in the periodic table of elements, krypton is a noble gas, so it's in group 8. It has 36 electrons, alright, and let's see which statements are correct. The 1s and 2s orbitals have the same energy, they have different sizes. That is immediately wrong. How can 1s and 2s have the same energy? That's like stupid. So that means my answer is immediately, because I have crossed out 1, that means my answer is immediately C, is it not? But you know, you could look at them as well. The third energy level, n equals 3, has 3 subshells and 9 orbitals. So if I just write down the configuration of krypton, and the way to do that is my method of writing down electronic configurations is I write down S, P, D, F. I learned this from YouTube actually. 1, 2, 3, 4. So then I start with, because starts from the first shell, P starts from the second shell, D starts from the third shell, and F starts from the first shell, right? So 1s2, 2s2, 2p6. So you go in this order: SP, 1s2, 2s2, 2p6, 3s2. Because I have done this twice, so now I go back to 3s2, 3p6, 4s2. Am I doing this right? So it should be SS, and then PS, PS, so PS, PS, and then DPS, DPS. You're going in that order actually. 4s2, 3d10, and then 3d10, and then 4p. How many electrons do I have left to fill actually? 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 is 30. So I have 4p6. Alright, so that is the electronic configuration of krypton. So you start from 1 for S, and then S, and then you put 2 to P, SS, and then PS, PS, and then you go to D. So DPS, DPS, FDPS, FDPS. That's my method of solving it. Or you could draw the triangle as well. I just get confused with the triangle, that's why I use this method. But anyways, n equals 3 has 3 subshells and 9 orbitals. Let's see. So I have 3 subshells. Yes, I have 3s2, 3p6, which is and 3d10 actually. Yeah, so that is 3 subshells for 1, 2, 3, and so that statement is right. And 9 orbitals. Well, I have 1 here, I have 1 here, and then for P I have 3 orbitals, right? So S has 1 orbital, P has 3 orbitals, and then D has 5 orbitals. So 1, 2, 3, 4, 1, 2, 3, 4, 5. So how many is that? That is 9. So that's right as well. Now the 3D subshell has, because S has 1, P has 2 more than that, 3, and then D has 3 more than that, 2 more than that, 5, and then F has 2 more than that, so that's 7, right? And each orbital has 2 electrons. The 3D subshell has 5 orbitals that have the same energy together in an isolated atom. That is right. This is the 3D subshell, and it's 310, and they all have the same energies as other in the isolated atom, right? So dxy, dyz, dz squared, dx squared minus y squared, and did I miss one? Dxy, yz, x squared minus y squared, z squared. I'm missing one. Dx squared, y squared, dz squared, dx squared minus y squared. I don't know, man, but you get the point. 5. What are the names of the orbitals of the, even though you don't need this for AS level, what are the names of the orbitals? So it is dxy, dxz, dxy, dxz, dyz, and dx squared minus y squared, dz squared. Alright, cool. Now the next question, which is question number 32. The group 4 elements, carbon, silicon, and germanium, can all exist in the giant molecular structure, which is also found in diamond. The bond lengths in these structures are given below. Why does the bond length increase down the group? So let me just write down group 4. I do not have group 4 memorized, so let me just write down from the correct table. Alright, I don't know why I do this, it's just a habit. Why does the bond length increase on the group? Because orbital overlap decreases on the group. That is right, because your atom becomes bigger, so then your your intermolecular distance increases, right? If your bond length your orbital overlap decreases, your bond length increases. Atomic radius increases on the group, that is right as well. And nuclear charge increases on the group. No, it doesn't. Nuclear charge does not increase on the group. Wait, doesn't it? It does increase, definitely it does increase, obviously, because you have more protons, so the charge in the nucleus does increase, but it doesn't cause the bond length to increase. That is a less significant factor in determining the bond length than is the atomic radius. So the atomic radius increases so much that the increase in nuclear charge is negligible, not negligible, I shouldn't say negligible, but has less significant of an effect on the bond length. Alright, so I hope that makes sense. And yes, nuclear charge increases, but that is a less significant thing in determining bond length than is atomic radius. So your answer is B. The periodic table is here. Okay. Next question. NaClO3 is used as a non-selective weed killer. On careful heating, this reaction occurs. 4 NaClO3 gives NaCl plus 3 NaClO4. On strong heating, this reaction occurs. NaClO4 gives NaCl plus 2O2. The overall reaction is 2 NaClO3 gives 2 NaCl plus 3O2. What do these equations show? Okay, so let me just, they're talking about oxidation states and blah blah blah, so I'll just check what are the oxidation states of chlorine in each of these compounds. So Na has a fixed oxidation state of +1, oxygen here is -2, but there are 3 atoms of oxygen, so -2 times 3, plus X, and we take chlorine as X is equal to 0 because the overall compound charge of the compound is 0, so that becomes X minus 6 plus 1 equals 0, so X minus 6 plus 1 becomes -5 is equal to 0, so then X is equal to +5, right? So this is sodium chloride 5, +5, and over here you have -1 because N +1 and -1 becomes 0, and then for NaClO4 I'll do the same thing, which is Na has +1, oxygen has -2, 4 atoms, so that's -8 overall, and plus X is equal to 0, so X minus 7 equals 0, X is equal to +7, right? It is +7. Let's do that, but actually you don't need to do that below because we've already done it, we've already calculated before. So NaClO4 is +7 here and -1 here. Minus looking so weird, and over here NaCl over here is +5, and over here is -1 again. So NaClO3 can behave as an oxidizing agent. Well, in fact it is undergoing disproportionation reaction, which means it is also, you know, becoming oxidized and also becoming reduced by oxidation state. So it can behave as an oxidizing agent as well as a reducing agent, both of them, because that's what's happening in this reaction. It's becoming self-oxidized as well as self-reduced. So that's, sorry, not this should not be the arrow. This should be the arrow. Self-reduced, so self-oxidized and self-reduced, right? So the oxidation numbers of chlorine in the 3 compounds shown are +6, +8, and -1. No, I've got +5, -1, and +7, so that is wrong. +5, +7, and -1 is wrong, and so my answer is 1 and 2. That means my answer is B. All right. I know that section B is not a part of the syllabus, and like it's not. The question papers are just 40 MCQs and not section B, but I still like to use to solve it because it's just good practice to learn things and stuff, I'll also give you an idea of more types of questions they could ask, and that doesn't mean, I mean to say maybe they could even ask in question, even in the new format they could ask questions like you have 1, 2 and 3, and then A 1 and 2, B 2 and 3, C 1 and D 1 and 3. They could even ask questions like that, right? So section B is still a useful section in my opinion. All right. Which statements correctly describe an effect of a rise in temperature on a gas-phase reaction? More particles now have energies greater than the activation energy. That is right. Just remember your Boltzmann curve, right? And then the energy distribution profile changes with more particles and more potential energy. That is wrong. With less particles having the most probable energy. Why? Because see, if I draw my Boltzmann curve, I have, for example, initially it was like this, right? And now my temperature is increased, so now my Boltzmann curve has shifted to the area and the curve is still the same, but my Boltzmann curve has shifted to the right, and the peak has lowered as well, perhaps become a bit flatter as well, but lowered. This is my energy and number of molecules, right? Roughly I'm labeling it. So what is the most probable energy? The most probable energy means the peak. That means the most number of molecules have this energy. So at that, initially this was my most probable energy, but now my most probable energy, like the peak has lowered, right? So that means my most probable energy has lowered as well. So so my most probable energy has lowered, in fact, now that my temperature has increased. And the activation energy of the reaction is decreased. No, it hasn't, because for example, my activation energy is here. My activation energy is still there. It's just that more particles have energy greater than or equal to activation. So the area of this has increased rather than just this. It's now all of it, right? So my number of particles having energy greater than or equal to activation energy is increased, but the activation energy has not decreased. My answer is D. Right? Which statements concerning the group 2 elements magnesium, calcium, and barium are correct? It's just a habit, I told you. I just write down all the things. That's an Urdu mnemonic for you guys, but yeah, this is the stuff, this is the thing. And which statements are right? The reactivity increases with increasing relative atomic mass. That's true. The reactivity increases deep down the group, and the relative atomic mass also increases down the group. The oxidation number exhibited in the stable compounds is +2. That's right. Group 2 tends to have +2 oxidation state, fixed usually. On strong heating, their nitrates give off oxygen only. No, they don't, because for example, if I just write down a random group 2 nitrate like X, NO3 twice, I'm just taking it X, so that'll be XO plus 4 NO2, or in fact, let me just take it as 2 NO2, and I'll balance it with half O2. So 2 NO2 plus half O2, right? So that gives me nitrogen dioxide as well. So that means this is wrong, and my answer is B. Great. Next question. Sulfur dioxide is used as a food preservative, and the reason for that is that it, they've given the reason here, in fact, behaves as an antioxidant. Which statements about sulfur dioxide are correct? It's to behave as an antioxidant. That's right, because what does antioxidant mean? It means behaves as a reducing agent, and that is why sulfur dioxide is used, because it, prevents, it reduces the oxygen in the food, so that means that the aerobic bacteria cannot respire in it, so it kills the bacteria that could, so it inhibits the growth of mold and yeast again. Yes, so it helps preserve the food that way, because it's reducing the oxygen in the package, and so it is preventing oxygen from being there in the package. It's a reducing agent and antioxidant, and so aerobic bacteria are not there to respire on the food and stuff, and so the food remains fresh. Aqueous SO2 contains SO3, so these 1 and 3 are all immediately right, which means 2 must be right as well, but if you want to see it, then aqueous SO2 means SO2 plus H2O, right? Contains SO3 2 minus ions, but that is H2SO4. Is it? No, it's not H2SO4, it's SO2, so O2 plus O plus SO3. H2SO3, and what is that? That is, you can write it as 2H plus SO3 2 minus, right? You can rewrite it like that, because it's H2SO3 if you consider that acids dissociate and stuff, right? So as that does contain SO3 2 minus, because H2SO3 is the same as H plus and SO3 2 minus, and 2H plus. So that means that is right as well, so my answer is A. Okay, next question now. An oxidizing agent that can, an oxidizing agent that can oxidize ethanol to ethanoic acid or to ethanoate ions, which means ethanoic acid or ethanoate ions. That's just if you do the base, react ethanoic acid with the base, then you get ethanoate ions, right? Will also oxidize methanoic acid to carbon dioxide and water. Which reagents on heating will react differently with HCOOH? I'll just draw it out, and CH3COOH. So you have CH3COOH as well. I'm just drawing it like this because I like the carbons to be attached to the carbons, right? So Na2CO3 should react with both the same, because they're both acids, fundamentally, aren't they? So it will react with the H to give you HCOONA and H3CCOONA and half H2, right? So this will not react differently, it will react the same, which means immediately my answer is C. But let me check the other options again. Fehling's reagent is a test for aldehydes. CH3 CH3COOH will fail the Felling's reagent test. But HCOOH, the thing that's beautiful about it is that it sort of has a aldehyde group as well. See this part of it, so it's like RCOH, right? That's the aldehyde group, and it has that. It has RCOH, or you can say RCHO is a better way to say it. In fact, RCHO. So it has RCHO. So that's why it will react with. So it will give a positive test with Felling's reagent, which means it gives a brick red precipitate with Felling's reagent. So that means that this gives a positive test, this gives a negative test. So they do react differently with the reagent that reacts differently with both of them. And now we have dilute acidified KMNO4. HCH, again, CH3COOH will not react with KMNO4 because it cannot oxidize. KMNO4 will not be able to oxidize COOH. But for this one, again, because it has an aldehyde group, sort of, RCHO, so that means that this can be oxidized to, well, actually it will be oxidized to carbon dioxide and water. Over here, you're gonna get carbon dioxide and water. I'm not sure where it exactly breaks because I haven't, like, I don't remember actually, but the point is it forms carbon dioxide and water. Should it be here? Anyways, this will give you carbon dioxide and water. I should probably research what exactly the mechanism is for this to go to that, but it forms carbon dioxide and water, and this one will not react, so that means these reagents react to the answers. Okay. Next question, question number 38. Each of the compounds below is treated separately with excess of NaBH4, the product of which reaction is then treated with excess of concentrated H2SO4. So NaBH4 is a reducing agent, so that means that if I react it with NaBH4, what will I get? Well, this will get reduced to OH, and my aldehyde will also get reduced to OH over here, right? So that's what I get. Again, over here I will also get OH, and again I will get OH here, and this will also become OH, and again this will become OH. So they're all reduced. Because NaBH4 is strong enough to reduce them, it's not strong enough to reduce carboxylic acids though. Now the product of each reaction is then heated with excess concentrated H2SO4, which basically means you are dehydrating the OH. So you're dehydrating the alcohol into an alkene. So if I dehydrate it, the thing is over here I will get one bond like this. So if I remove my OH, then this carbon atom that is attached to OH will will have a double bond with another, the adjacent carbon atom, which is just one carbon atom in this case, right? So I get this basically downward direction. I get this. My hexagon drawing is so beautiful, right? But then for this one, it can form, because it has, this carbon has two adjacent atoms, right? This one or this one that is carbon. So I can form either this thing that I've drawn here, where it's like this, right? Or I could form this thing. Okay, so I get two here. They want only one final product, so this is immediately out, because if you count it from here, for example, 1, 2, 3, 4, so this is all the 3 and 4, the 3 and 4, the double bond is between 3 and 4, but over here I have 1, 2, 3, 4, so the double bond is between 2 and 3, so that means it's not one final product, so that means my answer is immediately C. Alright, but you can wait, I'm reading the question right. In each case, one or more products are formed with the molecular formula C with one formula, one product with which compounds give only one final product with the molecular formula C7H10. Yeah, I'm right. I am right, am I not? I think I'm right. So the answer should be C, but let me just check the other ones out as well. Again, over here you get this when you dehydrate the alcohol, but over here you get either this or you can get this. The thing is that these are the same. See, 1, 2, 3, 4, 1, 2, 3, 4. These are the same, 3 and 4 and 3 and 4. So the double bond is between 3 and 4 in both cases. So that means 2 is right. It satisfies the condition that only one final product. And if I look at 3, again this will get eliminated to give me this, and the double bond here But one double bond can be here, can it not? So I get one double bond, like one thing like that, where 1, 2, 3, so the double bond is between 2 and 3. But then the other one is this. But the problem here is that here, if this carbon atom is bonded to 1, 2, 3, 4, 5, it has 5 bonds, which is wrong. It cannot have 5 bonds, so that means the only product will be this. So that means this also has only one final product, which means the answer is C. Alright, so yeah. Next question. Which reactions result in the... I'll just erase this stuff so that I have space. Okay, but I hope you understood that. Oh, this is a much longer video than my first one, but it's okay. I put timestamps as well, so that I will put, inshallah, timestamps, but you can navigate the video easily. Which reactions result in the formation of propanoic acid? So we have CH3, CH2, COO, Na plus H2SO4. So this is a salt and this reacting with an acid. Will that give me propanoic acid? It will, because this has 2H plus and SO4 2 minus, right? So it's possible for one H plus to go there and this forms Na2SO4. That is very possible. So that is true. The first one is right. Second one is this thing reacting with MnO4 minus, which means you're oxidizing it, so this breaks, this bond gets ruptured, and so you get ethanoic acid. Wait a second. Yeah, you get ethanoic acid, and since the same thing will happen on that side as well, so you get 2 moles of ethanoic acid from one of this. But that's ethanoic acid, not propanoic acid. Over here I have 1, 2, 3, so that's propanoic. I will get propanoic acid, right? But for this one I get ethanoic acid, so that means 2 is wrong. And now the third one is CH3, CH2OH, and I'm reacting that with Cr2O7, so I'm oxidizing the alcohol, so that becomes, God, my drawing skills are so bad. Anyway, so that becomes, well, 2 carbon atoms still remain, and then because it's the same thing, right? 2 carbon atoms, and then you get OH. So again, you get ethanoic acid, not propanoic. So my answer is D. Done. Right. Next question, which is the last one. I have the structure of propanamide. Which statements about the hydrolysis of propanamide are correct? Can be hydrolyzed by heating and replacing H2SO4, which is acid hydrolysis. And then I have base hydrolysis here, and then the last one is just hydrolysis without a catalyst, which will be very, 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 very slow, and it doesn't really take place easily, and I would say that it doesn't take place very easily, so I can eliminate that option, can I not? So my answer, I would say, like, if I look at it from a surface level point of view, my answer should be B. And if we test out the options and thoroughly hydrolyze it, basically you need certain conditions for it to hydrolyze. It can't just hydrolyze with cold water. You need it to be acid hydrolysis or base hydrolysis, like acid aqueous, base aqueous, and so if I do it with H2SO4, well, this should be the bond that's broken, am I right? Yeah. Even in that case, like the HCOH case, this one should have been the one that's broken. I'm not sure, but I think so. I'm not sure. Anyways, whatever, that breaks, and so what do you get? You get NH3, and you get CH3C, CH2, COOH, right? But then if you have this is the rough thing you get, but then with acid hydrolysis, since you're hydrolyzing with an acid, so you have an acid, so that means your NH3 will react with the acid to give you NH4 plus, and so because you have H2SO4, so you actually get NH4 twice SO4 plus your propanoic acid that you have over here. And if you're talking about base hydrolysis, this NH3 will remain NH3, but your propanoic acid in this case will because you have Na, right? NaOH. So then your propanoic acid will become the salt, so it will become sodium propanoate, so COONA. So that's what happens in acid or base hydrolysis. But with cold water, you need certain conditions. It can't just be cold, and cold water especially, bro. Like, come on, no. So the answer is B. Okay. And yeah, the paper is done now. That was a fun paper, quite long. I think it's like even like I guess what. Perhaps like half an hour longer than my first video, or maybe a bit more than that, but it was fun. A bit, I don't know if it's a bit more than that. I mean 27 times 2, approximately half an hour longer than my first video, but it was fun. Hope you all benefited from that, and